Hi, I'm Jim Burnham. Welcome to Chapter 13 on electrons and electronic configuration. In our last chapter, we talked about the behavior of gases and we developed the ideal gas law. In this chapter, we're going to talk about the development of atomic theory and how we believe electrons are arranged in atoms. So let's talk about various models of the atom. So far, we've talked about the atom as a nucleus containing the protons and neutrons surrounded by electrons. Now this is a simplistic model and explains some things, but not everything. Let's go back to the evolution of the atomic model. We begin with John Dalton's model, often sometimes known as the bowling ball model or the solid sphere model. This was the idea that all elements are made up of atoms, which is true. All atoms of a given element are identical. That's not quite true now that we know about isotopes. Atoms can't be created or destroyed. That's generally true. All atoms of one element have the same mass. Again, isotopes make that not quite true. Atoms of different elements combine in small whole number ratios to form compounds. That's true. Now, Thomson, with his cathode ray experiments, discovered that atoms had negatively charged particles. So he called them electrons, and he considered that maybe they were embedded within a positive sphere. To balance each other out. This gave rise to what is known as the Plum pudding model, or the blueberry muffin model, where the electrons are mixed in with the positively charged matter altogether. But then Rutherford came along with his gold foil experiment. He bombarded gold foil with alpha particles, expecting them to pass right through, but some of them bounced back, sometimes at massive angles. And so he said there must be very, very tiny, dense centers to atoms. And so he called this the nucleus. And the rest was basically empty space. So this was the resulting model of Rutherford's experiment, a nucleus surrounded by negative electrons. Now, this gave rise to a very important question. I mean, if electrons and protons are oppositely charged particles attract each other, so why don't the electrons collapse or fall or get pulled into the positive nucleus? So Niels Bohr came up with the idea that electrons had to have specific energy levels, leading them to move in certain orbits, and as long as they stayed in those orbits, they wouldn't gain or lose energy. So they wouldn't spiral into the nucleus or fly off away from the nucleus as long as they stayed within their specific energy orbitals. So this explained also why sometimes, when you bombard atoms with energy, they would give off light. This explained what is known as the photoelectric effect. And that is explained because electrons, when they absorb energy, get promoted up a level, and then when they drop back down, they give off a specified quantity of light. So this is the Bohr model of the atom, and it's still useful today, as we're going to see. But it was superseded by the cloud model, or what is known affectionately as the mechanical, what's it called here? I forgot, the quantum mechanical model of the atom. And in this idea, the cloud model, the electrons don't orbit the nucleus like planets. They can be found anywhere in a cloud-like region, what we call a probability region around the nucleus. They move so fast that we can't really detect them directly, and we can't tell where they are or where their speed is without distorting it. So this is the modern atomic model. That again, we have a nucleus containing protons and neutrons, but the electrons are in a cloud-like region around the nucleus. So this is a quick overview of where we've come from Dalton, his bowling ball model, to Thomson's plum pudding model, to Rutherford's dense nucleus, to Bohr's energy level orbitals, to Schrodinger's electron cloud model. Now, the laws that identify these regions where the electrons are most likely to be found are beyond the scope of this class, happily. Here's Schrodinger's wave equation that shows the probability of a single electron being found along a single axis. Happily, we don't have to worry about that. You may have heard of the Heisenberg uncertainty principle, which says we can't simultaneously find both the position and the speed of an electron. So you can find out where it is, but not where it's going, or you can find out where it's going, but not where it is. Now, in the quantum mechanical model, we're going to talk about energy shells and energy subshells. And this is a depiction of overlapping subshells. So here, this tiny sphere is the 1s orbital, and that's surrounded by the 2s orbital, and then that's surrounded by the 3s orbital, but within that third shell, we have some subshells. So we have the 2s orbital, but we also have the 2p orbital. And as you can see, the s orbitals are shaped like spheres. That's kind of nice and simple and clean. But the p orbitals are shaped like dumbbells. And as we're going to see, increasing orbitals not only have increasing energy, but they have increasingly weird shapes. So every time we go up an energy shell, we go up an energy level, and we have more and more subshells within them, and many of them have weirder and weirder shapes. We talk about a quantum of energy, and that, as we said before, is a packet of energy, a specific amount of energy required to move an electron from its present energy level to a higher one. It's also the amount of energy that the electron will give off when it descends back from a higher energy level to a lower one. So we describe an electron's behavior or likely location with 4 different variables. And the first one is to describe its energy level. The second one will describe the shape of the orbital. The third one describes a particular suborbital, and the fourth one is going to describe its spin, the spin of the electron. We'll go through these rather quickly. It's just important to know that they exist. There's 4 principal quantum numbers. As we look at the periodic table a little bit later on, we're going to see that there are basically 7 energy levels, 7 energy shells of increasing distance from the nucleus. So this is the first energy level. That will correspond to period 1 in the periodic table. This is energy level 2, 3, 4, and so on. And each one is increasingly further from the nucleus. The second quantum number equals the number of sublevels, and we name those sublevels in this order: S, P, D, and F. And the L number, the third number, designates the shape of the electron cloud. So this is how many orbitals. An orbital is a space for electrons. Every space can hold 2 electrons. So every orbital can hold 2 electrons. So S has 1 orbital, holds 2 electrons. P has 3 orbitals, so it can hold 6 electrons. D has 5 orbitals, holds 10. F has 7 orbitals, holds 14. So as I mentioned before, the S orbital has a nice spherical shape. The P orbitals have dumbbell shapes oriented along the X, Y, and Z axis. And then D gets weird. You start to see donut shapes and double dumbbells. And then F gets plum crazy all the way around. The important thing to remember is that with every number, we have increasing energy. So the P is higher than the S, the D is higher than the P, and the F is higher than the D in terms of energy. Increasing energy and increasingly weird shapes. If you put them all together, here's what they look like. Here are the S orbitals, the P orbitals, the D orbitals, and the F orbitals. Finally, we talk about spin, because we have to distinguish between the 2 electrons in the same orbital. Remember, every orbital holds 2 electrons. But we have to be able to distinguish each electron from every other. So we have to give them different spin. And so we describe the electron's spin as either clockwise or counterclockwise. Now this leads us to the Pauli exclusion principle, and that is that no 2 electrons in an atom can have the same 4 quantum numbers. Just like no seat in a stadium can have exactly the same identifiers. So whenever you pick a seat, it's going to have a unique way to identify it from every other seat in the stadium. It might be section E, row 12, seat 8. And that tells you that each seat can only hold one individual at a time. Well, same thing. When we name each electron, it has to have a unique set of quantum numbers. They can't all 4 be the same. And so the last way we distinguish them when there's 2 in the same orbital is with spin. So how many electrons can be in a sublevel? Well, in the S, it has 1 orbital, 2 electrons. P, 3, 6, we talked about this, 5, 10, 7, 14. Now these are the 3 important rules to know about filling out orbitals and subshells. The first is the aufbau principle, and that means we start with the lowest energy levels first before filling higher energy levels. This makes sense. These electrons are going to want to go to the lowest possible energy levels first. The Pauli exclusion principle says we can have a maximum of 2 electrons per orbital, and paired electrons in the same orbital, must have opposite spin. And finally, we have Hund's rule that says when we're filling electrons, we're going to put single electrons in separate orbitals in a sublevel. So if we have the 3p orbitals, for example, we're going to fill those one at a time. 1 electron here, 1 electron here, 1 electron here, and then, and only then, will we double up with an opposite spin. So we'll put this spinning up, spinning up, spinning up, and then on the 4th one, spin down, spin down, spin down, for a total of 6 in those 3p orbitals. This is an orbital filling diagram, and so if we wanted to build this up, so the first electron here we put in here, that would correspond to hydrogen. The second one we would put pointing down, and that would correspond to helium. Then we would come back here to lithium, 1 up, and then whatever's the next one, down, and so on. So we would fill these 1 electron at a time, 1, 1, 1, 1, 1, 1, and so on. This is a mnemonic for helping us to fill orbitals correctly. We're going to start with the 1s's until we get to 1s2, then 2s, until we get to 2s2, then 2p6, then 3s2, 3p6, 3d10, 4s2, 4p, and so on. We're going to fill them this way. We're going to fill them starting with 1s, 1 and 2, and then 2s2, and then 2p6, and then 3s2, and then 3p6, and now kind of unexpectedly 4s2 before we go back to 3d10. Then 4p6, 5s2, 4d10, 5p6, 6s2, and so on. 4f14, 5d10, 6p2. So this helps us get the correct filling order because the 3p and the 4d are so close, or the 4s and the 3d are so close that the 4s's fill up before the 3d's, even though they're in what you'd think this would be at a higher energy level. But they're very, very close, and so this takes care of that. This is the unexpected way in which it fills. So doing this, we can build up the entire periodic table. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and so on. Now we identify various parts of the periodic table by their electronic configuration. So this group here is the S1 group, and this would be the S2 group. So together this is the S block. Here would be your 2p's, and since there are 6 of them, this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So this would be considered the P block. Helium, even though it's over here, is considered part of the S block. So sometimes you'll see it stacked over here with its other S compatriots. The transition metals are known as the D block, and the intertransition metals are the F block. Here's another way of depicting this, and this shows the levels. So here we're at the 4, right? So this is energy level 1, 1s1, 1s2, then we bounce down to 2, 2s1, 2s2, then all the way through P6, 3s1 and 2, then through P6, 4s2, and then we start the 3ds. We have 10 elements in the 3ds, and then we go back to the 4p's, and so on. So just another way of looking at the various blocks. Here's the S block, here's the D block, here's the P block, and here's the F block. Now, even though we know that the quantum mechanical model is more accurate, and that it's much more accurate to talk about electron clouds of probability and orbitals, and that models that we need to treat electrons more like waves to explain the properties of atoms, as the quantum mechanical model does, we still, in spite of all of the power of the quantum mechanical model, we still find it useful to use the less accurate Bohr model and to talk about electron orbits and to keep track of electrons like planets, even though we know that's not really what's going on. We know the quantum mechanical model is much more accurate, but we still find it useful to use the Bohr model and to talk about energy shells and then to really keep track of each electron in each shell. And so when we do that, we can see, so here's each electron depicted in each shell. So this is 1s1, 1s2. Everything, this has, a 1s2, but now we're adding a 2s1, and now we're adding a 2s2, and now a 3p1, 3p2, 3p4, 3p5, 3p, oops, sorry, I missed one here somewhere. P1, 2, 3, yeah, okay, so p1, p2, p3, p4, p5, and p6. And then we start over again, right? So sodium has everything that neon has, but we're starting over with another electron shell, another 1s. So this is how we would keep track of electrons using the Bohr model as we go through these various families. And as you can see, we have names for them. This is the alkaline family, alkali earth, the boron family, the carbon family, the nitrogen family, oxygen family, halogens, and the noble gases. All the magic happens in the outermost electrons, what we call the valence electrons. So it's this outermost electron that's going to react, not these inner ones. It's this outermost electron that's going to react, not these inner ones. It's these two outer electrons that are going to react, not these inner ones. Not these, just these. And so sometimes we will keep track of the valence electrons all by themselves, because it's the valence electrons that determine the chemical behavior of elements. So oftentimes you'll see it just like this. We'll just say, look, we're just going to keep track of this one outer electron. We're just going to skip writing these in because they are not the ones that are part of the chemical magic. And so here is just a simplified view of the electron configuration where we just keep track of the outermost electrons. Notice that in group 1, there's one valence electron. Group 2, 2, group 3, 3, group 4, 4, group 5, 5, group 6, 6, group 7, 7, and group 8, 8. At least everything lower than helium. So you'll often also see this depicted with what is known as Lewis dot structure. And again, Lewis dot structure only keeps track of the outermost valence electron. So here's lithium with one valence electron. Here's sodium in the same group, one valence electron. Beryllium's got 2, magnesium's got 2, boron 3, aluminum 3, and so on. So these are blank orbital diagrams that help us fill out, and remember, we use our three principles, right? The aufbau principle, we start with the lowest orbital energies first. Hund's rule, we fill them one orbital at a time until we have to double up, and when we double up, we use the Polyexclusion Principle, and we give them opposite spin. So here's how we would do some of the electrons using these orbital diagrams. Here's lithium, it's got 3 electrons, so we're going to put one here, one up, one down, that's 1s2, 2s, one up. Beryllium has 4, we're just going to take this figure and then we're going to put one down and fill up the last of the 2s. Then we're going to start filling the 2p. One up, another one up, another one up, and then only then will we go back and start filling in the opposite direction. So here are elements 3 through, well, with some skips, through 11. Now, as you would expect, there are going to be some exceptions to the filling rules. So there's 2 main exceptions that we hit them at elements 24 and 29. So up to 23, everything follows the aufbau principle order, just as you would expect, lowest first, one at a time, and so on. But when you get to chromium and when you get to copper, you have an exception. And what you see here is rather than them having a 4s2, 3d1, 3d2, 3d3, 3d4, because it's a half shell, it doesn't want just to have 3 separate d orbitals with 1 electron each. It wants to fully fill that half shell. That's funny, fully fill the half shell. So it pulls an electron from the 4s2, leaving it to be a 4s1, and then it puts 1 electron in each of the 5 d subshells. Same thing happens with carbon. When it gets here, you would expect this to be 4s2, 3d9, but it pulls 1 extra electron, pulls that electron from the 4s to completely fill up the d shell. So what we see is that a half-filled d shell and a fully filled d shell is more stable than a fully filled 4s shell. And so that leads us to these 2 exceptions to our aufbau filling order. And we also see that in other places within the transition metals. But this is the first place that it happens, and so it's an important exception to know about. So the point here is that filled energy sublevels, at least when it comes to Ds, are more stable than partially filled sublevels. So that's generally true. Now the half-filled are not as stable as filled, but they're more stable than other configurations. And so that's why in this case, the chromium atoms and the copper atoms are more stable with only 1 electron in the 4s sublevel, so that they can have a fully half-filled D subshell or a fully filled 3D subshell. So just remember, there are exceptions. Chromium and copper are the first 2. Okay, if you have a blank periodic table, there's a really great coloring project that you should do to help you organize your table. And the first thing to do is to put the numbers outside. These are your main energy levels. And we're going to number the rows. This is going to be energy level 1, 2, 3, 4, 5, 6, and 7. And then we're going to add some more row numbers here starting at the D. So at row 4, we're going to make this 3D. And then we're going to go back to 4 Ps. So just look at this. So this becomes 3, 4, 5, and 6. 1 number less than you'd expect from the principal energy level. And then we go back to the principal energy level. And then down here, we're going to drop it 2 rows down. This is going to be a 4, this is going to be a 5. Now we're going to move helium over to hydrogen. No need to color it yet, but we're moving that over here because helium is part of this S block. And now we're going to start shading these in. So pick a color and shade all your S block elements, 1 color. And then pick another color and shade all of your P block elements. Then take another color and shade all of your D block transition elements. And And then finally, with the last color, shade all of your inner transition, your F block. So this is your S block, one color, your P block, another color, your D block, a third color, and a fourth color for your F block. That's it. Thank you.